climate change, marine life, and the carbon cycle. How do they interact? This fundamental question has been driving our research of the marine biogeochemistry team. I am Eun-Young Kwon and have been working at ICCP since 2017. I was also privileged to join as a ICCP faculty last year. On behalf of my ICCP colleagues, some former members, and the external collaborators, I would like to take you on a journey into our research and share with you some of our important discoveries. Out of 31 publications produced over the last 8 years on this subject, I would like to highlight 5 key publications in this talk. Those highlights include the phytoplankton responses to 21st century greenhouse warming, and the glacier and interglacier changes in the global carbon cycle, and the role of marine life in the oceanic carbon sink. Phytoplankton are photosynthetic microbes that are drifting in surface waters. They fix about 50 billion tons of carbon every year, a process called net primary production, or NPP. Through photosynthesis, phytoplankton convert inorganic carbon and nutrients such as phosphate and nitrate into organic materials. And those organic materials sustain marine ecosystems and lowers the CO2 levels in the surface water and the atmosphere. Therefore, future changes in ocean NPP are crucial for climate and life. Despite its importance, future changes in ocean NPP remain highly uncertain. So here I show you the projection from multiple Earth system models participating in the coupled model in the comparison projects. The solid line and the dotted line show the multi-model averages, whereas the shading shows the inter-model variability. So according to this simulation, the globally integrated ocean NPP could either increase by 5% or decrease by up to 15%. Those overall declining trends results from the projected ocean warming, which strengthens the upper ocean stratification and reducing the CO2, reducing the nutrient supply to surface water, and thereby the ocean NPP declines. The question becomes, the primary productivity is truly sensitive to the nutrient availability in surface waters. So here I plotted the observed phosphate concentration in the top and the primary productivity in the bottom from station Aloha. So we can see that in the 2000s, the phosphate concentrations were really low, even below the P-stress threshold. During this time period, the primary productivity persisted. Our further analysis of the data revealed that during the 2000s, when the surface waters are depleted in phosphate, the carbon to phosphorus ratios of phytoplankton increased from 150 to 250. What happened during this time period was that the phytoplankton continued absorbing CO2 while minimizing phosphate uptake. This adaptive strategy by phytoplankton is known as the stoichiometric plasticity. And this plasticity contributes to the spatial distribution of the carbon to phosphorus ratios of the phytoplankton community. So here we used an inverse model of ocean biogeochemistry to constrain the carbon to phosphorus ratios of sinking organic particles using the observed nutrient data. And what we found here is that in the oligotrophic waters where the surface waters are depleted in phosphate, then the C2P ratios are as high as 300, whereas in the eutrophic waters, where these waters are enriched in phosphate, then the C2P ratios are lower at 90. In order to investigate the role of the plasticity in future ocean MPP, we performed sensitivity experiments using the community Earth system model. So in the orange and red experiments, we enabled the nutrient uptake plasticity by phytoplankton. And in the blue experiments, we turned off the plasticity. The results were just striking. So when we allowed the plasticity, then the model projects the global ocean MPP to increase slightly by the end of the 21st century. Conversely, when it turned off the plasticity, the MPP substantially reduced. And this divergence in future projection is consistent with other Earth system models. So when we group the models into the two, red group incorporating the full plasticity and the blue group without the plasticity, we found a similar divergence. The MPP study here focused on the annual averaged MPP. However, the biological processes in the ocean are highly seasonal. So our former postdoc Ryuhei Yamaguchi used an GFDL Earth system model to study how the planetary warming can influence the seasonality of the phytoplankton biomass. So here I show you the example from the subpolar North Atlantic. The blue curve is the present day climate seasonal cycle, and the red curve is the future. And what he found is that in a present day climate, the phytoplankton biomass begins to increase in late February when the rapid shoaling of the winter mixed layer supplies abundant light and nutrients to phytoplankton. Then the biomass peaks in late May, just before the zooplankton grazing surpasses the phytoplankton growth rate. So by the end of the 21st century, ocean warming is going to cause both initiation and the bloom peak to shift earlier. This earlier initiation is because of the earlier onset of spring and the inability of zooplankton to keep pace with the accelerated phytoplankton growth. The earlier bloom peak is caused by the increased metabolic rates of zooplankton, which increases the grazing pressure. The earlier occurrence of the bloom peak is mostly pronounced in the Arctic Ocean and the mid to high latitudes of the Northern Hemisphere. Conversely, the bloom peak is projected to be delayed in the Equatorial Pacific Ocean and along the Southern Ocean. And this delayed bloom peak is associated with a warming-induced lengthening of the phytoplankton growing seasons. When the phytoplankton die and sink, the sinking organic materials are eaten by heterotrophic organisms, such as bacteria and fish. In this process, the organic carbon is decomposed back into inorganic carbon, and this can transport carbon from the surface ocean to the deep ocean, and is called the biological carbon pump. And this pump is responsible for the downward gradient of dissolved inorganic carbon, or DIC. So here I plotted the present day distribution of DIC, the depth averaged concentration on the left, and the zonally averaged concentration on the right. So the section runs from the North Atlantic to the Southern Ocean, then to the North Pacific. So we see that most of the biologically sequestered DIC is stored in the deep Southern Ocean and the deep Pacific and also deep Indian Oceans. And this is because of the longest residence times of the deep waters to accumulate the carbon from biological pump. Then the DIC-rich deep waters can upwell to the surface through the Southern Ocean by the upwelling of circumpolar deep water. And part of the upwelled DIC gases to the atmosphere through air-sea gas exchange processes. And climate change can influence those CO2 outgassing by altering the overall intensity and the sea ice extent. And those processes have been hypothesized to explain large changes in atmospheric CO2 concentration during the glacier and interglacial cycles. So here I show you the reconstructed concentration of atmospheric CO2 over the last 800,000 years. So the CO2 concentration was lower at 180 ppm during glacial times. However, it was higher at 280 ppm during interglacial times. And the magnitude and timing of those changes are among the biggest mysteries in climate science. Our former researcher, Carl Stein, used an intermediate complexity Earth system model to study how the climate system responds to the orbital forcing and the observed atmospheric CO2 concentration over the last 800,000 years. He first estimated the air-sea interaction timescale modulated by the sea ice extent, which is shown in blue. Then he also estimated the Southern Ocean stratification indicating the overwhelming intensity, which is shown in red. Based on those estimates, we used an offline carbon cycle model to calculate the atmospheric CO2 concentration. We found that those two processes can lead to a 40 ppm reduction from the interglacial to glacial transition. What's remarkable from this study is that the earlier strong reduction was dominated by the effect of ocean stratification that traps more carbon in the deep ocean while outgassing less into the atmosphere. Then this was followed by a prolonged and slower effect of the sea ice that caps more CO2 under the extended sea ice. And I would like to point out that our estimated CO2 reduction was only half the observed CO2 reduction from the interglacial to glacial time. One of the missing processes in our model was the positive feedback from the calcium carbonate compensation. So many part of the marine organisms can build calcium carbonate hard shells and skeletons, and those calcium carbonate can sink into the ocean's interior along with the biological pump. Then part of it dissolves in the water column, and the remaining is buried in marine sediments. We realized that even for the present-day climate, the key driver for the water column dissolution is poorly constrained. So we used an inverse model of ocean biogeochemistry to constrain how much is exported from the surface, and how much it dissolves, and how much is buried in marine sediments. What we found most interesting in this study is that globally, about 40% of calcium carbonate exported from the surface dissolves in the upper 300 meters of the water column. And those waters have the chemical properties that are not favorable for the dissolution of calcium carbonate. So what's really happening here is that the biological respiration within the twilight zone, they produce CO2, and also they make the microenvironments where the calcium carbonate can dissolve. So this process is responsible for the dissolution of up to 80% on regional scales. When the calcium carbonate dissolves, this generates the excess alkalinity. And some of the excess alkalinity can overwhelm to the surface and increase the CO2 buffer capacity. And this turns out to contribute to about 20% suppressed outgassing through the low latitude of the global ocean. And this process has been overlooked in many Earth system models, and we are going to explore the role of the water column as well as the sedimentary dissolution of calcium carbonate in the long-term changes in the global carbon cycle as a future study. Other ongoing and future work includes the global warming effect of the extreme ocean temperatures, especially in marine protected areas. And also we are currently exploring the fish biomass responses to the climate change. And also we will have 2 new members joining us in March, and they will explore the role of the mesoscale eddies in the oceanic carbon cycle and the marine life. And also we will explore the marine habitat changes of marine organisms from the deep past to the future. And thank you for your attention, and I'll be happy to take your questions.